my pleasure to everyone present. It's my pleasure to introduce Mike Klein, who is here with us today giving the ITC Colloquium. Mike did his undergrad in the University of Wisconsin.
Go Badgers.
And then he did his PhD at Chrtien.
Go Beavers.
And after that, he was a postdoc at the University of Santa Cruz.
Banana slugs.
And then NASA him.
Yep.
And now, of course, he's an assistant professor in the School of Earth and Space Exploration at Arizona State University. Mike is an expert on modeling the atmospheres of brown dwarfs and exoplanets and in studying the chemical composition, origin, and the ensuing implications for atmospheres. So without any further ado, let me hand it over to Mike.
Thank you guys for having me out here and for the opportunity to tell you about exoplanet atmospheres. So I know some of you guys are experts in this, so if at any point during my talk I say something that sounds BS-y, feel free to call me out on it. So here's the obligatory, there's a lot of exoplanets plot. And so, right, why do we want to study exoplanets? There's a lot of them. And so while we can't get a lot of information on any given individual planet, we can use the fact that there's a lot of planets to kind of piece together the properties of planets as a whole. So it's just kind of illustrating some key properties we can get just by measuring the planet size and the planet mass. We can say something about the planetary density, which can give us a sense for what maybe the bulk composition is. And so there's tremendous diversity within the exoplanet population, both in terms of their temperatures, there's lots of different colored dots here, but then also their densities, okay? But just measuring their planet, the planet size, the radius, and the mass, and the temperature, that's not enough. What we really want to do is we want to start digging into the details of individual planets in the ensemble of the entire planetary population. And for that, we want to study the planetary atmospheres. And so philosophically, I think that the atmosphere is really the only observable portion of an extrasolar body. And so all of the information that we're going to learn about exoplanets, most of the information that we're going to learn about a given exoplanet, is going to come from its atmosphere. So if we want to understand the processes happening on a planet, we're going to have to understand their atmosphere. So why exoplanet atmospheres? What are some of the key questions we want to address here? And this is just a few. There's kind of an infinite list of things we want to know. But some of the big ones that we've been focusing on as of late have been the idea of connecting something about a property of a planet back to how it formed. What is the climate diversity within the population of extrasolar planets? What are their temperature ranges? What are the weather like on these worlds? How does planetary chemistry change across this diversity of planets? And then, of course, aiming at eventually in the future, characterizing biosignatures or finding biosignatures, what even is a biosignature. It's the same as Earth. So I just kind of want to go through kind of the key hypotheses or interesting questions in each of these areas first to sort of set the stage here. So the kind of cartoon picture, more or less, that's the broadly accepted mechanism for planet formation is this so-called Chrtien Mechanism, where you start out with some dust and gas within a protoplanetary disk that forms some pebbles, some magic happens, you form some boulders, and then you can grow these sort of larger 10-ish Earth mass type embryos, which then become large enough to accrete substantial amounts of gas. And so one kind of prediction of this formation mechanism is that as you go towards lower mass planets, so things that are kind of in the Neptune-ish kind of mass range, and then here this y-axis here is the, think of this as the metal enrichment, so the amount of not hydrogen and helium in the atmosphere. As you go towards these lower mass planets, you might expect that the envelopes that they accrete are less massive, and therefore they're more subject to infalling planetesimals, which can then kind of enhance the metallicity of the atmosphere. So here's kind of a prediction from one of these planet formation models that suggests that you would expect increasing envelope metallicity as you go towards decreasing mass. So this is something that we could measure in a planetary atmosphere across a range of planetary masses. Another hypothesis, this is plot is shown all the time, and it's also very old now, but it kind of illustrates the idea that depending on where you formed in the protoplanetary disk, the further away you form, you could be subject to the influence of the different ice lines in a protoplanetary disk. So as you get further out, the volatiles condense, leaving behind gas that is depleted with what that condensable formed out of. So if you go beyond the water ice line, you would be leaving behind kind of water-rich gas. If you go further out, oxygen, carbon-rich gas. If you go even further out, you have even more carbon-rich gas. So you would expect that if you have planets forming out here, and if they migrate inwards after that gas dissipates, you might expect that those envelopes could be enriched in carbon relative to oxygen relative to what you would expect the stellar abundances to be. So there could be some imprint of these ice lines in the planetary atmosphere. So metallicity and carbon to oxygen ratio could be diagnostic of the planet formation process. An alternative hypothesis for, say, what the ratio of carbon to oxygen might be in the atmosphere is that if indeed you are bombarded by these icy planetesimals, things made out of water ice basically, falling into the planetary atmosphere, you can add that oxygen back in, and in fact, instead of having carbon-rich gas in your envelope, you end up having oxygen-rich gas in your envelope. So you have kind of two, in a sense, competing ideas for what the distribution of elemental carbon to oxygen ratio might look like in the planetary atmosphere. So this is kind of a two hypotheses that we can test. So kind of the questions from planet formation that we might want to address. Yeah.
On that background plot, I would have thought, yeah, that first one.
This one.
That the enhancement of the metals versus the blue, which I think are hydrogen and helium.
Oh no, these are different. These are different size planet. Ignore the blue dots and the red dots.
Oh, okay. I thought
Yeah.
you were.
Yeah. Sorry. It's these models kind of break down as you go lower than about 10-ish Earth masses here. So the blue dots and red dots are just indicative of the different size planetesimals that would
But I
fall.
would have thought that the enrichment of the heavier elements relative to hydrogen and helium would be explained by the fact that in the lower mass planets, you preferentially lose hydrogen and helium. They don't have the gravity to hold them, as well as the more massive planets.
Right. So in this regime, you're going to be subject to, say, photoevaporation and things like that, or just
So it's not an enrichment, it's more a depletion of the hydrogen and helium.
In this regime, yes, but in this regime here, it would be an enrichment. Yeah. So there's a bunch of stuff going on over here, and I'm saying in this regime, this is what we kind of care about right now. So that's a very good question. Does that make sense?
Yeah.
Okay, metallicities, C to O's, these are things we'd like to measure in a planetary atmosphere. Whether or not you believe any of these formation mechanisms and the predictions they make, these are still diagnostic of those processes. Other things that we're interested in are planetary climate, right, for Earth, right? We want to understand the global energy balance. What's the input flux of the Earth? What's the outgoing radiation? The Earth's atmosphere acts like a heat engine, so effectively this is going to drive weather and climate within Earth's atmosphere. So understanding the balance of each of these components of input energy and energy coming out is kind of a key in terms of understanding the kind of the global climate of a planet. If you look at thermal structures in all of the solar system planets, so right here this is pressure, proxy for altitude, so higher altitudes up here and temperature down here. Sort of a trend that we see within our own solar system is all of the temperature profiles seem to turn over and increase with increasing altitude, so-called stratospheric inversion. Different mechanisms are causing that in the solar system planets, right? Earth, it's ozone, and then we think it could be hazes and a little bit of methane in some of the Jovian worlds. Point is, there's some diversity in the thermal structures within our own solar system, so we want to ask, do we have a similar type of diversity in the thermal structures in extrasolar planets, specifically in highly irradiated exoplanets? These are the things that we can study now, because they're easier. How do the thermal structures behave with things like gravity, temperature, composition, things like that, and can we measure that? Can we determine that? And then finally, this is a little garbled down here, we can even measure, we can measure the sort of the flux coming off of a planet with time, and if we have spectroscopy, those different wavelengths are probing different depths in the atmosphere due to different optical depths. And so we can probe the temperature as a function of depth and latitude. So we can effectively do what weather satellites are kind of doing around Earth, monitoring the time variation of the planet as a function of space, so depth and say longitude right here. So we're getting to the point where we can start to piece together planetary climate on these worlds. And so if we look at a lot of planets, yeah, what?
You mentioned the geology effect of the temperature structure, but there is also volcanoes that can change the composition of the atmosphere. here.
Um,
So how would you disentangle that?
Right, so things like the Jovian planets, we don't have to worry so much about volcanoes. But for the rocky planets, yeah, I'd imagine if you had a situation where you had a Pinatubo happening on your terrestrial planet around Trappist, whatever, yeah, you could inject sulfates into the atmosphere, which could in principle change the thermal structure. And so if we were to observe a lot of those planets, maybe we could say something about, I'm making things up now, we can maybe say something about the rate of volcanic, explosions or something like that. Probably not, but yes, there's going to be surface factors that play into controlling the thermal structure in these atmospheres. We don't know because we have Earth, right? This is why you want to study a lot of them. Okay, and then finally, coming back, I guess, to what you pointed out, we want to understand the chemistry. So what are the chemical mechanisms, the dominant chemical mechanisms operating in a planetary atmosphere as a function of temperature, gravity, or radiation, all of these things. What is the relative role of transport in governing the distribution of molecules in the atmosphere? What is the role of photochemistry and transforming molecules from their major reservoirs into sort of trace species and maybe driving cloud formation? What is the role of clouds? How do clouds behave with kind of bulk planetary properties? Again, kind of information that we can only get by looking at a broad range of objects to provide that kind of lever arm in these different regimes in terms of understanding which mechanisms are going to matter the most. And then finally, one could argue that one of the prime reasons why we're studying extrasolar planets, I don't think it's the prime reason, but is to assess habitability and figure out whether or not we're alone. And so one way of doing that is by looking